excellent talk on 1D electronics, and now we will be moving to 2D photonics. And it gives me great pleasure to introduce Associate Professor Goki Eda. Goki is truly a global citizen. He was born in Japan. He grew up in India. He did his degrees in the US. He then went to the UK, and finally he's in Singapore. So Dr. Eda received his master's in MS in Material Science and Engineering from the Worcester Polytechnic Institute in 2006, and a PhD in the same discipline from Rutgers in 2009. Incidentally, his supervisor, Manesh Chawala, is also an associate editor of ACS Nano. Subsequently, he became a Newton International Fellow of the Royal Society of the UK, and he worked at Imperial College in London. And he joined the NUS as an assistant professor of physics and chemistry and a member of the Center for Advanced 2D Materials in 2011 as a recipient of the National Research Foundation Research Fellowship. And I happened to be dean then, and we suddenly talent spotted him, and he has lived up to his name as a rising star. He has won many awards in the past decade. He's been Singapore National Academy of Science Young Scientist Award, University Young Researcher Award, the IPS Omicron Nanotechnology Award, and he's also an associate editor of the NPJ 2D Materials and Applications. So today, Dr. Eda will tell us about building novel photonics with 2D materials. Over to you, Goki.
Okay. Thank you very much for the kind introduction, Andrew. I hope everyone sees my computer screen, my presentation.
Not yet.
Okay, great. So thank you. It's my great honor to be presenting here. And I'm very excited to be standing in this virtual podium. This is my first experience. And I'd like to thank Paul and Alice for the kind invitation to this seminar series. So today I'll give a brief talk on photonics of 2D materials.
Ed, you didn't share your screen.
It's not shared? I'm sorry, I thought. Okay. How about now?
Great, yes.
Okay, fantastic. All right, so yeah, so I'll talk about photonics of 2D materials. And okay, so I'll just start by introducing where I am. Andrew introduced to the Center for Advanced 2D Materials. This is the center that was just launched when I joined NUS about 9 years ago. And it's really been an incredible experience to be part of the center with all these talented colleagues. So a lot of the words and success I've enjoyed in the past few years, the credit really goes to many of the collaborators, because without them, I really couldn't have made the progress I did make. So, so this is a center I'm part of, and we have great colleagues, and the center is directed by Professor Antonio Castroneto, and these are just a picture of some of the affiliated members of the center, but there are many, many more. But there are lots of exciting collaboration opportunities in this center, and I've truly been enjoying that opportunity. So, Prof. Wu just discussed electronics and how electronics has made an incredible advance in the past several decades. But photonics has also made tremendous advances, and there are many, many examples of the advancements of photonics. But a lot of the advancements of photonics really boils down to advances in the synthesis or growth of semiconductor quantum wells, which is really the heart of many of the photonic devices that we rely on these days. One example is typical example is a laser, which also enables this fast broadband communication, which we rely on to have this type of online virtual seminars. And another example, which I really like, is this technology called vertical cavity surface emitting laser, or VCSEL, which is something that you already have in your hand if you have a phone with a face recognition technology. So if you look at your phone, there's a beside where your camera is, there is a tiny dot that has in which there is this VCSEL embedded inside, and that VCSEL is made of these semiconductor quantum wells, which generates infrared laser, which shines on illuminates your face, and another infrared detector would monitor that. Well, will read the projection and identifies your face pattern. So this is just one of the many exciting photonics technologies out there. And as I just mentioned, semiconductor quantum well is really at the heart of many of these devices. And these are typically gallium arsenide or gallium nitride quantum wells with a thickness of a couple of nanometers, and existing growth technologies based on molecular beam epitaxy or metal organics chemical vapor deposition are so mature that we are able to grow these quantum wells, hundreds of layers or thousands of layers of quantum wells at over large scale at relatively short time. So here's a typical picture of a semiconductor cross-sectional TEM of a semiconductor quantum well. Now, we know that these technologies are quite mature and they're commercial, and quantum wells are very useful, but there are still technological barriers. For instance, there are fundamental reasons as to why the quantum wells cannot be made atomically smooth, because thermodynamically it's impossible to have atomically perfect interface between, for instance, gallium arsenide and indium gallium arsenide. And this is a major problem in both electronics and photonics, because, for instance, in the case of electronics, the charge transport or mobility of electron gas living in these quantum well layers drops with the roughness of the well to the power of 6. So it's very sensitive to, especially the charge transport is extremely sensitive to the roughness. And similarly, if you have, well, those who are working on quantum cascade lasers, they, one of the problems they have is these fluctuations in the thickness of these quantum wells, because if you have slight variations in the quantum well thickness, the energy levels will change, and that will slight misalignment can really change the decay dynamics of the excited states. And that's one of the reasons why quantum cascade lasers is still not been perfectly miniaturized to the extent that other lasers has been miniaturized. So when the two-dimensional materials were first reported to exist, so these two-dimensional materials, by 2D materials, these are materials, atomically thin materials that are derived from van der Waals layered compounds, typically with Scotch tape, simply by mechanical exfoliation. So when the first report came out, it was very exciting, because these are natural quantum wells which have effectively no roughness on the surface. They're atomically smooth over long length scales. And what's even more exciting is that there are so many van der Waals materials with different chemical and physical properties with different band gap. And there are so many the opportunities for using or developing these layered materials or 2D materials, 2D semiconducting van der Waals materials for photonics or electronics application is very exciting. And on top of that, not only there are many materials available, they can be stacked into form heterostructures with no limitations on the type of stacking sequence or stacking registry. So again, one of the reasons why the lasers are limited to certain colors, for instance, is because of the materials limitation. We get red lasers and blue lasers and green lasers, but it's difficult to make lasers of every color, partly because of the materials. But if we can choose any materials we like, we can tune the band gap of the material and integrate into a device to achieve the desired optical or optoelectronic response or functionalities. And these layers can be stacked into heterostructures, just like in the case of van der Waals, just like in the case of molecular beam epitaxy grown quantum wells. So this gives us tremendous opportunities for future applications, both in electronics and photonics and many other disciplines. And the main materials family that we've been working with is this material family called transition metal dichalcogenides. These are dichalcogenides of transition metals, and there are about 60 different types of these compounds, but about 40 of them are layered van der Waals materials, and a couple of them exist fairly stably, such that we can simply exfoliate using Scotch tape and isolate a single layer of them. And especially these group 6 ones are semiconductors, and they happen to have a direct band gap, so they are very attractive for optoelectronics applications. So why do we think the 2-dimensional semiconductors derived from the van der Waals materials is different from quantum wells? Well, if you look at their optical absorption spectrum, the answer is quite obvious. So if you look at the absorption spectrum of quantum wells, you get this textbook type of step functions in the in its spectrum, which reflects the 2-dimensional density of states of quantum wells. Now, despite being two-dimensional, truly two-dimensional, these two-dimensional semiconductors don't give you the step functions in its absorbance. And this is because the excitonic contribution to absorption is much strong over electron hole pair generations. So the reason the excitons are stable, or excitons, which are elementary excitations in the material or bound electron hole pair, the reason they are stable is because of the strong Coulomb interactions. So this is a typical example of an exciton in a solid. So they are bound to each other. The electron and hole are bound to each other, and you cannot really represent their energy levels in a typical band structure, because the typical band structures are single particle picture. So we really have to look at the 2 particle energy levels. And it has this, if you have a quadratic semiconductor, quadratic band structure, you get quadratic band for excitons. Now, the reason why the excitons are stable in the 2D systems is because of the strong Coulomb interaction, which comes from the fact that the electric field that connects these charges, the opposite charges, can go around outside the 2-dimensional solid. So if you have a three-dimensional solid, the electric field is screened by all the electrons that are sitting outside the plane. But if you have a two-dimensional solid, the electric field is not screened, especially if you have a 2D material sitting in vacuum, because there are no electrons to screen these electric field. So this makes the binding energy of the exciton to be extremely high in two-dimensional systems and extremely stable, excitons to be extremely stable at room temperature. And one of the ways to demonstrate this effect is by looking at again, the absorption spectrum. So this is an absorption spectrum of a single layer MoS2 absorption in a transmission mode. And you can see these excitonic resonances at these energies. And these excitonic resonances give you absorption of close to 10%. So this single layer of MoS2, which is less than a nanometer thick, can absorb as much as 10% at these resonances. And if you go to even higher energies, let's say 2.8, 2.9 electron volts, they absorb even more strongly, absorb up to 30 to even 40%, despite the fact that they are less than a nanometer thick. So this is the result of excitonic resonances or oscillator strength concentrated in these excitonic resonances. Here's another demonstration to show the actual picture of a single layer suspended over a hole with a light illuminated from the back. So if you look at for instance, the blue light coming through the hole, you can see that just this single layer region will attenuate the light fairly well. And another reason why the oscillator strength is so concentrated in these resonances is because of this effect called band nesting. And this happens around the energy of about 3 to 2.8 electron volt, which are in blue range. So this is also the dimensionality effect. So if you look at the joint density of states of a two-dimensional material, you have this term, the gradient of conduction band and difference in the gradient of conduction band and valence band in the denominator. So if you have a region which is parallel, then you have this joint density of states term would diverge, which would mean that your optical conductivity or absorption also diverges. And this is what happens for many of these two-dimensional semiconductors, particularly group 6 TMDs. Okay, so that was about absorption, but emission is also quite prominent. If you look at single layer MoS2, it's much more luminescent, it's much more strongly luminescent than bilayer and multilayer counterparts. And this is related to the fact that single layer happens to be direct bandgap semiconductor, whereas its multilayer counterparts are indirect gap semiconductors. So it turns out that not only MoS2, but all the 2D semiconductors in group 6 with group 6 transition metals are direct gap semiconductors. So here's an example of WSe2 sitting on quartz. If you look at the sample under fluorescence microscope, you see this bright emission coming from only the single layer region. So whether it's a sulfide or selenide, this trend turns out to be true for these group 6 TMDs. So those are just generic properties of single layer TMDs, but because of the symmetry, because of the flexibility, because of the strong interaction between excitons and defects and excitons themselves, excitons with electric field or external particles, for instance, photons, there are many, the strongly excitonic nature of 2D materials, 2D semiconductors really open up avenues for novel photonics applications, which are otherwise not possible by conventional semiconductors like gallium arsenide, where the excitonic properties only kick in at very low temperatures. So whatever the applications, based on the excitonic properties of these 2D semiconductors, we really need to understand their dynamics and their life. So excitons don't live forever. When you excite these semiconductors, they form after you pump some energy to it, to the material. They can live for maybe picoseconds, nanoseconds, or sometimes microseconds, but they eventually die. And depending on what happens during their lifetime, the things that we can do will be quite different. In other words, if you can control the behavior of these excitons during their lifetime, we can achieve different types of applications. So one standard example is, for instance, to achieve power generation using heterostructure of semiconductors. Like if you have MoS2 and WSe2 van der Waals heterostructure, and this forms a type 2 band alignment. So when you form an exciton, then the exciton will dissociate at the interface due to the type 2 band alignment. And if you hook up electrodes to these sheets, then you can observe power generation or voltage generated at the interface of the material due to the dissociation. So this is an example where something happens during the lifetime. So in this case, the dissociation of electron holes happen during the lifetime of exciton, such that we can make use of the material. And it turns out that this dissociation process, or the charge transfer process, occurs in a very, very short period, typically picoseconds order. Which is almost comparable to the lifetime of excitons. It depends on the temperature, but almost comparable to the lifetime of excitons, such that we can, in principle, efficiently generate electron hole pairs or generate voltage in this simple device structure. But so our goal is to also to explore the dynamics of excitons, excited states, to see their implications on different photonics applications. So we have various activities in our lab. Here I'm going to just discuss our efforts in semiconductor or photonics device physics of excitonic semiconductors. One of the most successful technologies based on quantum wells is an effect. Well, it is an electro-optical modulators, which is based on an effect called quantum confined Stark effect. Sometimes this effect is called giant Stark effect, to contrast with the atomic Stark effect that you normally study in undergraduate quantum mechanics. But this is an effect where the absorption edge of a quantum well shifts as a function of the electric field applied in the outer plane direction of the quantum wells. And the energy of the absorption edge shifts quadratically with the electric field. And the reason it shifts is because of the polarization of the electron hole pairs in the quantum well, and the shifts in their energy levels due to the electric field. Now, this effect is called giant Stark effect, but we were curious to understand what this effect will correspond to in the case of two-dimensional materials. The reason we were curious about this is because, well, the two-dimensional materials are truly two-dimensional. So if you apply a vertical electric field, the excitons cannot polarize in the outer plane direction. So we were very curious to see if the excitons do polarize in the outer plane direction. Now, it's if it does polarize, and if you do get shift in the resonances, that will be useful for the electro-optical modulation applications. If it doesn't shift, it's also useful for well, diode applications in which the material is not sensitive to local charge fluctuations. This is a typical problem of diodes based on gallium nitride, where you have local electric field, which causes unintentional shift in the emission energies. But anyways, if you have a two-dimensional materials, what happens? Well, the energy should go quadratically, and it should be the prefactor for the quadratic term is the outer plane polarizability, and there is an analytical expression for that outer plane polarizability, assuming that you have an infinite square well. So this is a typical undergraduate quantum mechanics problem. Now, while we were wondering what would happen, there were several papers that were published, and what was interesting is that the numbers of reported for this outer plane polarizability varies over at least 2 orders of magnitude, which was quite curious because according to well, at least according to the prediction based on infinite square well, the outer plane polarizability should be of the order of 10 to the power minus 10, and Debye meter per volt. And this is smaller compared, this is much greater compared to the polarizability of hydrogen atom, which again you can calculate analytically. But we prepared our samples very carefully, such that we can control the charge density in the 2D material to see if there's any effect on screening. So this is a typical device design. So we have a single layer tungsten diselenide, which is sandwiched by an insulating hexagonal boron nitride, which is further sandwiched by a few layer graphene. And we have electrodes hooked up to each of these 3 layers, such that we can apply voltage between these 2 capacitors. Now, if we apply opposite voltages to this top and bottom gates, then we can study the effect of electric field. So with constant carrier density, whereas if we apply the same voltage, then we can study the effect of the carrier density at the constant electric field. So we fabricated a very high quality tungsten diselenide sandwich, which exhibits this extremely narrow exciton line width of about 5 milli-electron-volt. So what we found was in a way unexciting and in a way exciting. So here, when we apply electric field we applied the electric field up to more than 1 volt per nanometer. And what we observed is that there is absolutely no shift in the exciton resonance. Okay, the upper panels correspond to the effect of electric field for at the very low electron density. The lower panel corresponds to the same effect, but at higher, greater electron concentration. Now, in both cases, all the resonances. So here's a neutral exciton resonance, and here you have, on top of neutral exciton resonance, you have trion charged exciton resonance. So but all of these states don't shift with electric field, despite this extremely high electric field. So from this, we concluded that the outer plane polarizability is almost as small as that of hydrogen atom, which is to say that the electron hole pairs or the excitons are strongly bound to the metal sides, and they are not they don't get polarized, or they don't shift towards the Calcasian sides. So this really proves that the excitons in our 2D materials is truly two-dimensional. So it's not just us saying that these are two-dimensional, but they are physically two-dimensional. Now, having two-dimensional excitons is interesting because when you put one semiconductor, monolayer semiconductor to another on top of another, and you excite one of the layers, excitons in one of the layers, that exciton can induce another exciton in the neighboring layer, because the two materials are both excitonic, and there can be a strong dipole-dipole interaction. And the dipole interaction is strong when the excitons are parallel to each other. And this is exactly the condition that we have, because excitons are perfectly two-dimensional. So in both layers, the excitons are perfectly 2D and perfectly parallel to each other. And well, simple theory tells us that the coupling strength scales as 1 over the distance between these two-dimensional layers to the power of 4. So if we have these van der Waals heterostructures, where the two excitonic states can be spatially as close as possible to each other, the dipole-dipole coupling rate must be at its ultimate limit. So we were curious to understand if this dipole-dipole coupling rate is indeed at its ultimate limit. To measure this, so we fabricated this heterostructure, and essentially we studied its light emission. But because the band alignment is type 2, what happens is the charge transfer rather than the energy transfer. At least the dominant process is, one of the dominant processes is the charge transfer. Okay, so if you excite WS2, the hole goes. If you excite molyselenide, in this case, the electron goes to tungsten site. So that results in the quenching of the emission in the both layers, which doesn't give us too much information. So what we did is to vary the excitation energy gradually over exciton resonance energies. So here we have the excitation photon energy in the vertical axis, emission in the horizontal axis. This MO and tungsten represents the resonance energies of molyselenide and tungsten selenide. So what we see is that you have this vertical line here, which corresponds to the emission energy of molybdenum diselenide. So the emission of molybdenum gets enhanced when you excite molyselenide, when you hit the resonance of molyselenide, which makes sense. But what's interesting is that when you hit the resonance of tungsten sulfide, you also enhance the emission of molyselenide. So this is a strong evidence of energy transfer from tungsten sulfide to molyselenide. So we not only see if you look at the photoluminescence excitation spectrum, you not only see the resonance of tungsten sulfide, but you also see well, not only the ground exciton 1s, but you also see the resonance of 2s and 3s excitons. I will skip the details here, but what we learned by studying the rate equations is that the energy transfer rate happens in timescales of about 1 picosecond. Okay, so when you excite tungsten sulfide, what happens is the energy transfer, because of the energy exciton of tungsten sulfide is in resonance with the upper lying state, excitonic state of molyselenide. And there you have relaxation and emission of light. So we were aiming for the ultimate coupling strength, and that's exactly what we observed. So when we plot the energy transfer rate where in our case we have something of the order of 1 picosecond, it comes out to be something comparable to what you get in carbon nanotube bundles, where the energy transfer is also very efficient. But compared to the case of quantum Waals, gallium arsenide quantum Waals, for instance, the energy transfer rate is about 2 orders of magnitude higher. And this is solely related to the fact that the layers are close together and the excitons are truly parallel to each other. We explored this effect for heterostructures of chemically dissimilar materials. And this is an example of tungsten disulfide transferred on top of an organic-inorganic hybrid perovskite. So in this case, both have quasi-two-dimensional structure. But when you transfer tungsten sulfide on top of this perovskite, what we observe is the enhancement of emission in the region in contact with the perovskite, which again is strong evidence of energy transfer. What is interesting in this case is that what we observe is that the enhancement factor is more than what we had initially expected, because what we ended up observing is the way we could understand this data is only by invoking the fact that there are excitons living in different layers of perovskite, and each of those layers contribute to some extent to the emission enhancement in tungsten disulfide. Okay. Now, let me talk about, say a few things about devices. So if you look at the conventional light emitting diodes, you not only have the actual light emitting material, but you also have many other layers which are crucial for the working of the device. So these may be electron injection layer, the hole injection layers, the blocking layers, and so on and so forth. Now, this construction is crucial for realizing high efficiency devices. And if we want to achieve something like exciton polariton lasers, like it has been demonstrated for quantum well structures, we really need to make sure that the efficiency of the emission is optimized. So what will be the structure ideal for the light emission to occur? There's been several studies on this subject, several demonstrations of electroluminescence from 2D materials. But what we can see is that in most cases, typically for the vertical devices where the emission is in the planar mode, the threshold current needed to achieve light emission is typically of the order of microamperes, which corresponds to a very high generation rate of electron hole pairs. Now, what we can understand is that when you look at the electroluminescence efficiency, it should be a product. It's a product of essentially photoluminescence quantum yield, and another term which is probability for electron hole pairs to form an exciton. Now, this photoluminescence quantum yield is a material-dependent properties. So unless we optimize the materials, we couldn't do too much. There are some tricks, but we couldn't do too much, so we leave that. But the second term, the probability for the electron hole pairs to form an exciton can be tuned. So if the electroluminescence efficiency is much smaller than the photoluminescence efficiency, that means that there is something wrong with the device. And one of the ways to demonstrate this point is by looking at what is happening to imagine what's happening. So typically, when you make a sandwich structure, we inject both electrons and holes into the 2D material and hope that they form electron hole pair or excitons. But what typically happens is that they don't feel each other and they end up tunneling to the opposite electrodes. And only once in a while they form an exciton, and if we are lucky, they can end up emitting a photon. So we need to make sure that every charge that we inject should form an exciton. Now, to resolve this issue of low electron hole to exciton conversion efficiency, we looked into this device structure, what we call metal insulator semiconductor structure. So this is one of the earliest demonstration of electroluminescence that was done with cadmium sulfide. So we can make the same type of structure using van der Waals heterostructure. Okay, and when we did that, so we fabricated this MIS heterostructure. We indeed saw that there are we observe a strong rectifying behavior in this diode. It's essentially a tunnel diode, and as soon as we start to inject some current, we start to see electroluminescence. And so, if you look at the numbers here, you can see that even if we start to inject a current of something of the order of 0.5 nanoampere, the emission, we start to see emission. So the threshold is extremely low. The current density required for electroluminescence in this case is picoamperes, few picoamperes per square micrometers. So here's an example of our device. So this is our device, a sandwich of WSe2 with BN and graphene electrodes. So this is real-time observation of the light emission from our device when we apply a few volts across this across the boron nitride. So you can see that even with a current level of current density of 1.3 nanoamperes per square micrometers, we see fairly what we consider a bright emission. The reason this works is because, well, in the case of reverse bias, we have no current flowing. And this is because the boron nitride, which is a large bandgap semiconductor insulator, is forbids the tunneling of electrons. But if you apply forward bias, the electrons in the semiconductor layers cannot tunnel into boron nitride. But because of the band alignment, it turns out that the holes in the graphene layer can tunnel into the boron nitride and into the semiconductor layer, which always meets some electrons that are waiting on that side. So we always end up with formation of charged exciton, which always ends up emitting light. So this is a summary of quantum efficiency of PL and EL, and our devices show quantum efficiencies which are comparable to photoluminescence, which means that we essentially optimized the device configuration. Okay, I think the time-wise is I'm almost done. Could you? That was.
Yep, that's fine.
Yeah.
Okay.
Yeah.
So maybe So I'll a few topics to talk about, but I'll just skip some details and let me just go to the final slides. Okay. So I guess I took longer than I expected. Oops. Okay. So let me thank all my group members who did the hard work of making those devices, and all my collaborators. And yeah, thank you very much for your attention.
Thank you, Goki, for that excellent talk. And for those of you who have any questions, you can send them to, and I think the first question should be coming out soon.
Yes, let me put that up. Mm-hmm. Here.
Right.
Andrew, are you able to read that, or shall I?
I'll read that. Yeah. So the first question, Prof. Eda, as you said, monolayers MoS2 or WSe2 are attractive for photonic devices. Can you comment on the fabrication of these 2D monolayer materials over large areas?
Yeah, so thanks for the great question. So, so I didn't talk anything about the synthesis, but there's been significant progress in the growth of monolayer semiconductors, and there are ways you can essentially apply either metal organic chemical vapor deposition or molecular beam epitaxy to grow fairly high quality monolayers over 4-inch wafer scales. So it's becoming quite mature technologies, I would say.
Right. The second question, for heterostructure optoelectronics, how does one control the defects among different materials and structures?
Okay, so thanks for the question. So when you say defects, that could mean different things, especially for heterostructures. So one of the major issues of fabrication of heterostructures is the trapping of contaminants in between the layers. So these contaminants can be trapped during the fabrication of the heterostructures, and these are very difficult to remove. But there are ways to get around these problems. For instance, there's a technique called nano-squeegee method, which allows essentially you to push the trapped contaminants out of the away from your device region. Now, probably more important defects are the intrinsic defects in the material, which are typically sulfur or some chalcogen vacancies. Now, how do we control it? This is partly a thermodynamic problem. So you would need to grow these materials at particular vapor pressure of the chalcogen to minimize these chalcogen defects. But typically, these vapor pressures are difficult to achieve for instance, in regular CVD processes. So there should be either a way to passivate these defects, which are somewhat unavoidable, and to make sure that these defects don't undermine, compromise the properties that you want to achieve.
Okay, thank you. Goki, if I can ask another question to follow up on this one. So can you comment on the how developed is the transfer technology in order to minimize these defects in large areas? I say this because most devices made these days are by transfer methods. Or should we be putting more effort in direct growth methods like MBE or related methods?
So it depends on the type of devices that you want to achieve. Of course, the ideal scenario is to be able to grow the heterostructures bottom up, with just like one would do with MoS2 or MBE. But really, because of the layers that you need, for instance, I talked about the necessity of boron nitride, which is a good insulator. But the growth conditions for the boron nitride is very different, obviously, from the growth condition for other materials. So the direct bottom-up growth is not the easiest route to this issue. Now, the current transfer technologies, I guess, I think it's getting mature, and especially, well, these are typically, the leading research labs that are really making these, taking these transfer techniques to higher levels. But there are ways, for instance, to transfer inside the vacuum to avoid these contaminations. So I think that still needs a lot of work to make sure that we can reduce the defect density, or these trapped contamination type of defect densities below the limits of needed for some device applications.
Right, excellent. And thank you so much, Goki, for your talk. It was very instructive, and I think our viewers learned a lot from it. And right now, because this is virtual, I can't hand you this certificate, but we would like to present this virtual certificate in recognition of yourself being a rising star in this field and your, of course, support for the journal. Thank you.
Thank you very much.
Thank you so much. Now let's bring back Professor Hu, and we'll also bring in our third speaker, Professor Maria Lukatskaya, for a panel discussion. I'll give a formal introduction to Professor Lukatskaya after the panel, but let me just say that she's on the faculty at ETH, where she runs the Electrochemical Energy Systems Laboratory. And what we thought would be interesting for our viewers to hear is the three of you have had such spectacular starts to your career, each of you. And I think it would be interesting to hear how much of that, you were able to map during your training, and if there was something you could go back to in your training to do differently as advice you might have to our, to our audience of what that might be. And so maybe let's start with Professor Lukatskaya.
Thank you, Paul. Yes, this is very interesting question that you put out for our discussion. So with regards to mapping out the future, I don't think my path was very mapped out. So I got my bachelor's and master's degree from Moscow State University, and I actually was planning to stay in Russia, but accidentally I met Yuri Gogotse at one of the conferences, and he invited me for a short internship in his lab, which in the end transferred to doing PhD in his group. And again, at that moment, I was not as familiar with the PhD system in US, so I just really enjoyed interacting with Yuri. So I right away applied only to one laboratory, which was his. And only, I think, in the middle of my PhD, I realized, okay, actually, it is possible for me to continue do work in academia and maybe become a professor one day. And then kind of, I had a bit better plan for my future steps. So then for my postdoc, I went to Stanford and worked with Professor Jinan Bao. Actually, both Yuri and Jinan gave talks on this exact platform. So it is a great honor to also be giving a talk at the same platform as they did.
Yes, and actually Yuri's another of our editors, and Shanan's been on our editorial advisory board for many years now.
Yes, but with regards to advice, I would say there are a lot of resources at the moment, so it's definitely much better to start plan from early on, not rely on the chance, because not always you will have Yuri passing by your poster at the conference.
Although it turns out he travels a lot under normal circumstances, so the chances are not so small.
Yes, unfortunately now, yeah, it's not as common anymore. Yeah, but still networking definitely helps. And sometimes you never know from which door will open from your interaction with different scientists. So yeah, I think definitely I would advise to utilize all the opportunities to connect, including these online opportunities that we are currently exploring a lot. Yeah.
Excellent. And Professor Hu, you have the experience of returning to your home institution. And so tell us first about your trajectory, and then also if that poses any special opportunities or challenges for you returning to Eda. Oh, are you muted?
Yeah, yeah, okay. I think there's a big challenge when I return to Peking University because I just switched my research interesting several times. I should say when I was an undergraduate student, my major is astronomy. Yeah. Yeah. Okay. At that time, I think I was very interested about the physics, and it is a very I just happened to attend a lecture, and in that lecture, it was talking about the nanostructure, and I just think it's so amazing. Such kind of nanomaterials, and I still remember the thing they're talking about in the lecture is something called the seahorse-like fractal structure, and I still remember how beautiful the black and white picture of the TM image of such a structure. So I think I need to do something related to the nanomaterials. And I got a chance to start in the Peking University, to just move into the nanomaterials and the nanoelectronics under the supervision of Professor Lian Maopeng. And during my PhD career, and I get a lot of training about the device. And I do something like the sensors, and also it's my first time to do the things related to the carbon nanotube-based nanoelectronic devices. And then something happened. It is also another lecture. Attend another lecture, and it was delivered by Professor Zhongli Wang. And I was just attracted by the things he is talking about, the nano generator. So then after I finished my PhD, I go to the Georgia Tech, and I started to do things related to the energy harvesting technology, and also the things about the piezo photonics. I still remember, I just check it, and the first paper about the piezo photonics was published in ACS Nano.
Yes, that's right.
And Paul write the highlight for that work. So it's a great honor. And when I have the chance to go back to Peking University, I spent I think almost half a year, several months, to think about what I should start start in my own career. And I really think I have a good passion for the flexible electronics. And I know that there's a lot of researchers are doing things related to their sensors, their systems, but I think there's a critical issue about their information process units, the flexible IC. So I think I should do these things. And it takes us for almost, I think, 3 years to get the first paper published about this research directions. And also our first paper about the flexible IC based on carbon nanotube was published in ACS Nano in 2018. Yeah, and also this work was selected as the cover, the front cover of that issue. Yeah, so I don't know, but I think there's a lot of connections between me and the ACS Nano journal. Yeah.
Well, we hope there are even more.
Yeah. Okay. So I think the things led me to be here at current stage, I think it's the passion or the curiosity, the things I'm interested about. So yeah, I think I truly believe that one day the flexible electronics or the wearable technology will change the life of the person, not just our normal person, but maybe the person with disabilities. So yeah, I truly believe that. Okay, yeah, that's my story.
Okay, very nice. And Professor Eda, we heard of your travels during your training, and tell us something about how you chose those places, and ultimately also then ended up in Singapore with this very supportive environment. It looks like people working on 2D materials.
Right. Well, I think just like others, there was nothing that I had planned from the beginning. And I didn't have too many choices, partly because I didn't study very hard when I was an undergraduate, which I sort of regret. So if I can go back to my undergraduate or go back to myself, I could talk to myself as an undergraduate, I will tell him to just study harder. Well, so the reason, well, first I moved to Worcester, which was actually one of the very limited choices I had. And it was actually related to my sister, who happened to be going to a college nearby in Massachusetts. And I had really no idea exactly which schools I can, my ability back then would sort of would match up to. I applied to many top places and I was rejected. So I was very discouraged. But my sister just happened to suggest this professor in Worcester, WPI. And I went to talk to this professor, and he was interested in taking me on. And that's where I started to make some advance after after I didn't study too well as an undergraduate. But then I gained a lot of confidence when I was doing my master's because I knew I had to catch up, so I studied hard. I worked a lot in the lab, and at that time, it just happened so that my PhD supervisor, Manish Chawla, was looking for a PhD student, and it happened so that Manish knew my undergraduate supervisor, Ken Okano, who used to work as a visiting professor in Cambridge when Manish was doing a PhD student, was doing PhD. So there was some connection, and my undergraduate supervisor gave me a call, and he said, there's this professor at Rutgers, Manish Chawla, who is looking for a student, and I went to talk to Manish, and that's how I could move on to do my PhD. And yeah, I think that's where it started, I think. And yeah, coming back to Singapore again, this was not something I planned, but this is also partly a networking reason. And so Professor Chawla was, well connected to many scientists around the world, and one of them was Professor Lo Kianping Lo in chemistry department in NUS, and Professor Lo told Manish this opportunity of the fellowship, and Manish suggested me to apply for it. And I guess back then I didn't feel that I was ready to move on. Part of me said that I should be studying a bit more, and part of me also said that I should just get moving. And so I wrote the proposal, and I was lucky enough to get the fellowship. And there were many opportunities like that, and in many instances, I always felt that I wasn't enough, or I wasn't in the right stage to apply. So if I guess if any of the viewers who are in the early doing undergraduate or PhD or in doctoral postdoc stage, if there is an opportunity, I would say just give it a shot, because you never know if the opportunity will be available in a year after that your first opportunity. So yeah, many of my I think awards and fellowship that I won, I never knew that I could get it. So I never expected it. So I guess the chances can be higher than you think, is my advice to everyone.
So it seems like in all three of our rising stars, these passing connections end up being very important, and our ability to see each other at conferences, really made a difference. And so perhaps Andrew, do you have some thoughts on how we might get such connections going in this, in this year or so when travel is so restricted?
Yes, certainly. I think for like these virtual talks are an excellent idea to get to know people in the field, and it can be very effective because I have given, I think, 2 previous talks, one at a conference in India and another one I think was based in Hong Kong. And immediately after these talks, you get these PhD students writing to ask if there are opportunities in your lab and so on. So I think that although we can't travel this particular time, but we can really make use of these virtual conferences to tell the world about what we do and to look for opportunities. So my advice to students out there, please do attend all these talks. You never know what opportunities might turn up.
Well, I think then, as you say, it's also incumbent upon us to make sure we take this opportunity to connect out to the world, either through our own talks or with what Professor Alice Shang has done here in establishing this this weekly forum. Let's just maybe finish up on how it is each of you chooses students and postdocs for your groups. Because as Andrew said, now that you've had this big forum, you're going to be hearing from a lot of students and postdocs out and potential postdocs out in the world who will want to work in the exciting areas that you've discussed. And maybe we'll start again with you, Maria, Professor.
Sure. Yeah, I typically would say that what Yofan mentioned, that she had this drive to do science. So I would say this is, if I were to rank, I would put it at number 1. That the student has the drive to do science, is excited about it, and yeah, in most cases imagines this is one of the paths that they are very passionate about. Then I would say the overall knowledge and erudition. But for this, I think if you have a drive, you can build the knowledge and erudition. And equally important, I would say, creativity, that you can think outside the box and can see connections with the different fields that other people would not necessarily see right away. And I think in this sense, it's really excellent to attend the talks which are from the very different field of your own, because sometimes this is actually how you can actualize and see these connections.
Mm-hmm. Perfect. And you find?
Okay, because generally when we interview the students or postdoc, it's a very short time. So for me, and I think they, if they can thinking independently and be curious about the new things or new technology, it will be very charming for me, attracting for me, because when you're talking about something, some of the students will ask their own questions. That means they are really thinking about the things, and they have their own comments. I think that's very important. And also, I think maybe I think I don't know, but just in some times I just feel that yeah, I can have a very good say the I can just feel very comfortable to exchange ideas with the students. So maybe the chemical happened here. I don't know, but yeah, yeah,
Connect.
yeah, yeah.
Mhm.
That's the things from based on my case. Yeah.
I think sometimes people underestimate how important the social interactions are in relationship between trainees and an advisor, but it really makes a difference to feel comfortable being able to talk about
Yes.
science and life and and goals and plans. And it's different than just choosing an institution and saying, oh, this is a top university, or choosing somebody famous and saying, well, you know, people have been successful in that group, but you become part of an academic family that lasts your entire career, and being able to have that connection in a lasting and meaningful way, as you said, is something really important. It's important both for the professor to look for, but also for the potential student or postdoc. Right? And Goki, can you tell us what you look for when you try to recruit or filter, maybe a good word, potential students and postdocs?
Yeah, well, I think both Maria and Yufan raised the key points, but yeah, I think, well, the person, whether if you like what you do, I think that's great. Of course, you want to be good at what you do, but if you like what you do, if you like science with the topic, then I think you become proactive. I think you become more positive, and you can be more creative. And I think those are the qualities that I would look for. But I think that really boils down to whether you're whether you know whether you like it or not. And you know, that partly comes from the maturity of the person. You know, if you are mature enough, and this is very difficult to aim for. You can't really suddenly grow up mentally, but I think you want to look at yourself and know what you like to do. If you know yourself well, you know what you can do, and yeah, I think that sort of person who can self-reflect can be regarded, you know, someone reliable and independent. So I think that's one of the key qualities I would look for, on top of obviously, you know, good experience and knowledge.
Yeah, I think one of the things related to that's important to convey is it's important to get experience being a scientist in a laboratory, or if you're doing, you know, theory in that way. It's very different than taking a class. And you know, it's just as important to learn what you don't like as what you do, and you can often learn that very quickly in a laboratory as well. My own first research job lasted 3 hours. I realized that I wasn't interested in that kind of science, nor the associated smells. You know, and when we look for people, we often look for, have they been able to do science in some way, and that's much more relevant than test scores, or, you know, how you did in class as an undergraduate. You said, you know, the grades are much less important than really gaining the knowledge from those classes and from experience in laboratories. Andrew, how do you?
Yeah, so I must say that how I select students and postdocs has evolved through my 30-year career, because when I first joined NUS, it was a period of time where NUS was less known in the research arena. And we did have scholarships, and they were open to international students because we couldn't get enough local students. And so in those days, I, in a sense, left it to a committee to select students, and then they came to us. But these days, after so many years, I've graduated so many PhD students who are now professors themselves, and recommendations become a major route in which I get PhDs and postdocs. And I think these networks are very important, because they recommend, you get recommendations of people who whom they know would fit what your research objectives are. And I think these people would be successful PhDs and postdocs as well.
Much. Well, thank you to our entire panel. That was most interesting. And, you know, as you heard, though, that connectivity that we're trying to establish here is tremendously important. And we're figuring out how to do this one direction. We're looking for how we might go in the other direction as well. So I'll encourage you to reach out to our speakers and others who've been involved in ICANX. If something here intrigued you, of course, we always love to hear from people about our, you know, about their interests and to talk about ours. And so now what I'll do is we'll go on to our third lecture of today. This is from Professor Maria Lukatskaya, who you just met. She's an assistant professor at ETH, where she runs the Electrochemical Energy Systems Laboratory. You already heard that she got her PhD with Goki at Drexel and then went on to a postdoc with Jean Powell at Stanford. She works in the areas of new materials and electrolytes for energy storage and conversion, as well in electrochemistry, material synthesis, and materials characterization. She recently won the Environmental Energy and Science Lectureship Award, as well as